All right. Can everybody see the screen? Yes, okay, very good. Let's start. So this is the second class of matrix operations. Okay, and last time we went over matrix operations. This time we'll be going over some row operations. Okay, so this is our schedule. We're going to briefly review the hardest part of last lesson, which was basically the matrix multiplication. So we're going to review that. And then I am going to teach you about the Gauss-Jordan elimination, which is a very useful technique that we can use to solve systems with matrices. So let's just get started with our first homework problem. And this is basically just adding two matrices together. So I'm going to give you a couple moments to do this, and then I'll go over it. All right, so let's just go over this problem. Okay, so you have to add the two matrices. So let's check if that actually works. To add matrices, they must be the same size. So we have a 3 by 2 matrix plus a 3 by 2 matrix, which works, right? So first you have to It seems that adding the matrices is in parentheses, so we're going to add them first and then multiply everything by -5. To add matrices, all you're going to do is just to add the corresponding elements. So that should not be hard. We're going to have -5 on the outside here. This is a 2 by 3, a 3 by 2 matrix. So we're going to have 1 minus 5, which is -4. This is +4, -8, -3, a 10, and -2. Right, then we multiply everything by -5. So we have a 20, -20, 40, 15, -50, and 10. All right, so that's what we have. And that's how to solve this problem. So subtracting and multiplying by a constant is very self-explanatory. There's not much hard stuff to it. You just have to use operations on corresponding elements, right? It's the matrix multiplication is usually the confusing part for most people. So let's just see how we do that with the second problem here. So I'm just going to give you like 1 minute to do this, and then we'll come back and try to solve this. All right, so it's about been about a minute, so let's go back and try to solve this. So the very important part you need to notice when multiplying two matrices together is the shape. So previously, when you add and subtract matrices, or when you add or subtract matrices, they need to be the same size. But when you are multiplying two matrices, it's a bit special. So when you multiply matrices, they have to be in a certain form, which is M is the first matrix has to be like M by P, and the second matrix has to be P by N. Basically, the point is that the number of columns, right? The number of columns for the first matrix has to be equal to the number of rows for the second matrix. And as you can see here, we have two matrices here. One is 2 by 2, and the other is 2 by 3. So we are able to multiply these, right? Because this is equal, this is equal. So how do we multiply them? Well, when we multiply them, we have to basically have corresponding, let's see here. We have to have each row of the first matrix correspond with each column of the second matrix. So the resulting matrix here would be 2 by 3, basically this times this. So as you can see here, it's going to be equal to an m by n matrix would be the resultant matrix. And here we have a 2 by 3 resultant matrix. So let's see here, we have 3 and -3, and that's going to correspond to 2 and -6. All right, and that's the first element. So we can just go ahead and write that down. We're going to have a 2 by 3 here. The first element is going to be, let's see, 3 times 2 minus 3 times 6. Right, that's the first element. All right, then, all right, the second one, we're going to have this first row correspond with the second column. Right, so then we're going to have, well, let's see here, the second element of this row. So let's just make it bigger so it's easier to explain like this. It's just going to be 3, right, times 6 plus 3 times 5. So as you can see, this element corresponds with this element corresponds with this element, and we're basically multiplying them all together and adding them to make one element, right? And as you can see, the next one obviously would be these two, right? And you're just going to complete that until you finish the whole matrix. So we're going to have 3 times 1 plus 4 times -3. Okay, and then for the second row, you're basically starting from the second row of the first matrix, corresponding with the first column here, and the second column, third column, the same thing, right? So you're going to have 6 times 2 plus 3 times 6, 6 times 6 minus 3 times 5, 6 times 1 plus 3 times 4, right? So then matrix multiplication. This is the first element is going to be 6 minus 18 is -12. And it's easy to make mistakes at this point. So make sure to check out my work and see if it's correct. Next one is 18 plus 15. The next one is 3, right? Minus 12. Next one is 12 plus 18 is 30. 36 minus 15 is 21. 6 plus 12 is 18. So this should be the resulting matrix. All right, does everybody understand this? So if there are no questions, then I'm just going to continue on with our next homework problem, which is this. All right. All right, so let's go over this. And we can see the shapes of each of these matrices. We don't actually have numbers as the elements here, but we do have some variables that there's no like difference in that, and you're just going to do the same thing that you've been doing, just multiply, right? So let's look at the shapes of the matrices. We have one matrix that is 2 by 3, so 2 rows and 3 columns. Here we have one matrix that is 3 by 2, so obviously these can multiply, and the resultant is a 2 by 2. And now we can find all the corresponding rows and the corresponding columns, and then we can multiply. So let's just start. We're going to have a 2 by 2 like this. So it's going to be pretty chunky actually, since we have these variables here. I'm just going to make it big like that. We'll simplify later. So the first one, we're going to have these two, right? And then we're just going to continue in the same fashion. So 6u times, let's just start multiplying them already. So 6u times negative 3u is negative 18u squared, right? Plus 12u squared minus 6u cubed. That's our first element. And the second element in this row is 6u plus 6uv plus u squared v. So this is a very complex matrix here because there's so many terms, and it's probably not going to be simplified completely. But yeah, we don't have to worry too much about that. And then we have this is negative 3u squared v. This is 6 plus 6u v squared minus, well, plus 12 v squared u. Right, and then we have uv plus 3v cubed minus 2v cubed. Okay, and we just have to simplify terms now. So let's check. So we have negative 6u squared minus 6u cubed. That's our first term. Don't worry about factoring or anything. 6u plus 6uv plus u squared v. Our second term in this row. And then we have, can't actually simplify any of these. So let's just write them again. Right, so this is quite messy, but that's fine. There's some practice with variables, I guess. But usually we're going to be working with numbers anyways. So yeah, that's how we do it. So now we're going to review some matrix multiplication. And how exactly do we do that? So I'm just going to, again, review the shape that you need. The desired shape would be this, right? You have to have the same P, right? Then your resultant would be M by N, right? Pretty self-explanatory. And now to multiply them, they have to be in this format. To actually multiply the matrices, you have to look at the rows, right? So we have like a 2 by 2 here. Let's just say x1, x2, x3, and x4 times y1, y2, y3, y4. This would work because it's 2 by 2 times 2 by 2, so it does fit the shape, right? So it works. And to do this, we need to find the corresponding rows, right? And the corresponding columns, right? So this one and this one, right? And then we're going to multiply corresponding terms, add them, and that's our new element. And then our resulting would be like a 2 by 2 again. So I'm going to give you like about 1 minute to do this. This should be pretty easy. So just fill it out. And then we'll go back and check. Okay. Okay, so let's go over this. So remember that I said you have to have the corresponding rows in the columns. You're going to have x1 times y1 plus x2 times y3, right? That's going to be 1, okay? x1 is x1, y2 plus x2, y4, okay? We're going to have x3, y1 plus x4, y3, okay? You're going to have x3, y2, x4, y4. That's how you do it, right? So there's should clear us some confusion, right? That's about it, all right? For the matrix multiplication. Now let's look at some actual row operations. So augmented matrices. We're first going to have to learn about augmented matrices to start working on row operations. So let's consider the following system. Let's just say ax plus by is equal to c, all right? And then let's just say, actually, let's make this, what should we make it? Let's make this w and z, all right? So then we have cx plus dy is equal to z, okay? So now we have this system, right? So how do we convert it into a matrix? Okay, so we have a coefficient matrix. By removing the variables, we can have our coefficient matrix. That's going to look something like this. A, B, C, and D, right? You can see how the coefficients here become a matrix. We can also have a constant matrix, right? And then matrix is just going to be looking something like this, W and Z. Right? So you can see the constants right on the other side. And here we can have the coefficient and the constant. We can combine them to make an augmented matrix, which would model the whole system, right? It looks something like this: A, B, C, D, and then W and Z. So this straight line here kind of models the equation line. All right, so that's what this is. Okay, right. So that's what an augmented matrix is. So let's try to interpret some of these augmented matrices actually. So let's see here. Let me give you a couple of problems and you can solve them. And then I'll give you a couple moments to solve them. So like, let's just say 1, 0, 0, 1, 3, -8. B, just say 1, 0, let's say 0, 0, and then a 3 and -8. Okay. C, let's just say 1, 0, 0, 0, 3, 0. All right. So interpret these. By interpret, I mean how many solutions does each of these augmented matrices have? Okay. I'll give you like 30 seconds to do so. All right, so let's interpret what this means. So as you can see, once we have this augmented matrix, we have an x column and a y column. This is the x column, this is the y column, this is the constant column, right? That means when you have this is 1x and 0y. It's meaning that that's a solution for x. So we can see that x is equal to 3 and y is equal to 8. That means there's one solution. And this one you can see, well, in the second row here, 0, 0 is equal to 8, 0x and 0y is equal to 8. 0 is 8, which is cannot be true, because 0 does not equal to negative 8. That's just a false statement, and obviously that would be no solution. And finally, we have x is equal to 3, and then 0 is equal to 0. So this is one of the ones where we have infinite solutions, right? So x is equal to 3, and then this is infinite solutions. All right. Okay. So now that we know kind of what augmented matrices are and what to expect, we can now go on to some row operations. So what are row operations? Well, there's a couple of row operations, right? And there's actually 3, right? They're the main ones, and then we'll practice some, okay? So let's see here. The 3 row operations is swapping 2 rows. That's denoted by R. Let's just say capital R, actually, it's easier to see. I is swapped with RJ. All right, so these are just variable names for rows, right? Just variable names, not that important. Okay, so we also have, you can say a row is multiplied. Row is multiplied by constant. All right, and that's going to be k times ri to ri. All right, and finally, a constant multiple of one row is added to another row. So constant multiple of one row is added to another, right? And that's just going to be like k times ri plus rj is equal to rj. So basically, ri multiplied by the constant k was added to the row j. All right, makes sense, right? So now let's look at some examples that we have here. For example, let's just take this matrix, for example, 1, -4, 2, 4, and 3, -8. All right, so this is our example matrix, and we're going to do some row operations on it. So first, A here, we have row 1, right? This is row 1 and row 2. Row 1 swapped with our R2, right? This is row 2, right? When you swap them, you're just going to get 2, 4, 1, -4, and this is -8 and 3, right? Okay. Thus, you just simply swap the rows. You can also multiply a constant, for example, 1/2 of R2. Wait, let me see. Let's see, 1/2 of R2 is equal to R2. So row 1, of course, remains unchanged because we never did anything to it, right? But row 2 is basically halved. So we have 1, 2, and -4. Finally, let's say we have a -2 times row 1 plus row 2 is equal to row 2. So we had row 1, multiplied it by -2, and added it to row 2. All right. So let's see what happens here. So essentially, again, row 1 is not affected because this is affects row 2. So you're still going to have row 1 normally here. Row 2 is going to be affected because it's going to be basically -2 times 1 here is added to 2. So you're going to have 0. And then -2 times -4 here plus 4 is 12. And then -2 times 3 here added to -8 is just -14. Right, so that's how you do these row operations. All right, and make sure to put them in your notes. So I'm just going to give you a couple seconds to write this in your notes. Make sure you have it in your notes, okay? Now let's go on to some Gauss-Jordan elimination. So how do we actually do this? Gauss-Jordan elimination is using these row operations to basically solve a system, okay? So let's just take our system at the beginning. Let's just take our system at the beginning real quick. All right, and let's just try to solve it using Gauss-Jordan elimination. We had what? Let me write our system at the very beginning. Let me see. Which was it? It was we ever use that? Augmented. Oh, we never used that. Well, let me just think of another example. Let's say 2x minus y is equal to -7. X plus 2y is equal to 4. Okay, so now we have to convert this to a matrix, which is pretty easy, right? We convert this to a matrix. Just a 2, -1, right? -7, and then 1, 2, and 4, right? We convert that to a matrix. Okay, so now we use Gauss-Jordan elimination to try and solve this. Let's just start right here, right? So the ultimate goal of the Gauss-Jordan elimination is you have to get something like an identity matrix, which I talked about like last class. An identity matrix would be 1, 0, 0, 1, basically a diagonal column of ones and everything else is zeros. And let's say this is let's just say this is x1 and x2, right? So basically we want to get it into this format of an identity matrix because we can see that x is isolated, y is isolated, so we actually do get the values for x and y, and we have solved the system. So we have to get it into this form, right? We're going to have to get rid of one column here and one column there, right? One element, yeah. We're just going to have to like isolate each variable like that. So let's just start with the y's, right? So this is the y column, as we can see here. Let's just mark it real quick. This is x, y, and this is the constant. Start with the y's. Should be pretty easy. So you see -1 here. This is what I think they call it a pivot. I'm not sure what they call it. I think I remember they call it like a pivot or something. When you have something that is equal to 1 or -1, it's very easy to manipulate. So you can see that let's just say we did 2 times row 1 plus row 2 to row 2, right? And then let's write out the result. Row 1 is unchanged. Row 2, however, is going to be, right, it's going to be 5, and then 0, and then let's just say -10, I think, right? So you see 2 times this, well, no, 2 times 2 plus 1 is equal to 5, and 2 times -1 plus 2 is equal to 0, and then 2 times -7 plus 4 is -10. So as you can see, we already know what x is. We already know what x is because we have isolated this 5 here, right? And that's equal to negative 10. So obviously x is equal to negative 2, right? So all we need to do is divide this row by 5. Then we can get negative 2, right? Let's just do that later, right? We don't need to do it now, okay? And then for this next one, we have to get rid of this here, right? To get our identity matrix. Let's just actually convert it first. So 1/5 of row 2 to row 2, and then we're gonna have an unchanged first row, and then 1 0 negative 2. So we have another pivot here. We can use that to get rid of this 2 here. Let's just say we have negative 2 times row 2 plus row 1 is equal to row 1. Row 2, of course, remains unchanged, 1 0 negative 2, but row 1 is going to be negative 2 times 1 plus 2 is equal to 0, and then this still is negative 1, and then negative 2 times negative 2 is 4, positive 4 plus negative 7 is negative 3. So obviously, we can see that we have 1 0 negative 2. I'm just swapping the rows here just to make it clear. Then this is 3. All right, and then we can see that x is equal to negative 2 and y is equal to 3, right? Negative 2, 3 here. This is our solution. Through Gauss-Jordan elimination, we are able to solve the system like this. Well, you might be thinking that this is absolutely pointless at this point because you could have solved it using elimination in like 20 seconds, right? You could have solved this with substitution just regularly in 20 seconds, right? I could have, like anybody could probably do this in like a very short amount of time without doing all this gibberish with matrices. Matrices at this point seems like it's just messing everything up, right? For like these types of systems with only 2 equations, matrices is really a kind of unnecessary. You don't actually need to do matrices for these 2 equation ones. But when you have something like 5 equation, when you have something like 5 equation systems, then you're going to have to use matrices just to make just be much more organized. Because if you just try to solve the systems of 5 equations regularly using elimination or substitution, it's going to be very complicated and messy. So you're just going to have to use matrices to make it much more organized, much more faster, and much more efficient. But for example purposes, that's why I'm going to do 2 equation ones right now. And plus, we just learned about Gauss-Jordan elimination, so I'm not just going to give you a 5 equation matrices system for you to work with. So let's just start easy for now, and then we'll work up later on. Okay, so I'm just going to give you probably like a couple minutes to do this, and then I'll go over it. Alright, so let's go over this one. Let's just turn this into a matrix. Alright, so we have 5, -2, and 12, and 2, 3, and 1. Alright, so looks like we don't have any pivots, which is extremely disappointing. Let's see what we can do here. So first, let's add, basically, it's gonna be quite disgusting, but I think we can manage it. Alright, so let's just say we need to create a pivot, alright? Let's just create a pivot, okay? So we're gonna take -2 R2 plus R1, and that's gonna be equal to R1. So then we're going to create our own pivot here. Of course, row 2 is unchanged. We're going to have -2 times 2 plus 5 is just 1. So we created our own pivot, and then we have -8 here, 10. Next, we're going to have, say, -2 times R1 plus R2. So we're just going to use our pivot to get rid of some values here. So we're going to have the same row 1, but instead of 2, 3, 1 or anything, we're going to have 0 here, and then we're going to have, I think, 19 here, and this is -19. So as you can see, it works out quite perfectly. All we need to do is we have to take the 1/19th of row 2, and we're going to have 1, -8, 10, 0, 1, and -1. So as you can see, y is equal to -1. Finally, we need to get we need to use this pivot, right? This pivot to get rid of the -8 there. And we can do that by doing 8 R2 plus R1 is equal to R1. So then we get 1, 0, 2, 1, 0, 1, and -1. So as you can see, x is equal to 2 and y is equal to -1. So that's our solution. The next one. All right. So I'm going to give you a couple moments to do the next one, and now I'll go over it. All right, so let's go over this one. So we have clearly -2, 6, 6, 3, -9, -9. So first we can just actually do two operations at once. We're just going to have -1/2 of R1 to R1, and then 1/3 of R2. We're just going to simplify, right? So essentially, then we have 1, -3, -3, 1, -3, and -3, which is interesting, isn't it? Because we can just take R2 minus R1 to R2, and essentially we have 1, -3, -3, and 0, 0, 0. So what we have here is an infinite solution. Let's just convert the first row, right? Let's just take the first row and let's convert it back to equation form. So x minus 3y is equal to -3. And if we solve for x, we can clearly see that x is equal to -3 plus 3y. So then, if we set x, let's just say it's set y is equal to n. Therefore, the solution to this would be -3 plus 3n and n. As you can see, it's an infinite solution, right? All right, so that's all for today. So I don't think the Gauss-Jordan elimination is too difficult. It is definitely useful, but you won't begin to notice like how useful it is until you do like 3x3 systems or like 4x4 systems, in which case Gauss-Jordan elimination is much more useful than standard ways to solve, such as elimination or substitution. That's all for today, and I'll see you next time. All right, so actually, we have 2 more classes before winter break, so and I should be able to finish the unit by then, and that would be all good. All right, so I'll see you guys next time. Thank you for coming, and I'll see you guys.